Okay, going to go through the second part of this paper. The first part went through the first 6 questions, I think. So have a look if you haven't watched it, and then you can go through the second half in this paper. It's in the same playlist. It's along with the other May 2023 papers. Remember what I said, that there are 2 papers. This is the regional paper, so this is 1 PR. There's also the May 23, which is just paper 1P. So there's 1P and 1 PR. This is the Pearson Edexcel International IGCSE, which was used 2 years ago, May 23, and it's for physics and double award science, so it's the combined paper. If you're doing physics, you also will take a second paper, which will be paper 2, and I think the paper 2 is already uploaded in the same playlist. Okay, so if you liked the first video, don't forget to give me a thumbs up as well for this one when you start watching it. So I'm just looking for the right question that we got to, and we will start as soon as I find it. Okay, so I think it's here. So we did question 6. It was about the 60 ohm resistor. So let's just go back. Yeah, so we looked at that. Here's the mark scheme for question 6. If you want to stop the video and see how they gave the marks for the question we did in the last video. A, B, and then C. 14 marks for this question. Okay. Not much else to say on that. Then we're going to go through question 7. So I can tell it's going to be about nuclear physics because the unit of radioactivity is the becquerel, which just means how many nuclear disintegrations happen per second, named after Henri Becquerel, French physicist. And then they looks like they got an activity graph in becquerels and how it decays over time. Okay, so you should be plotting one of those, and then they got a nuclear balanced equation where the top numbers are mass and the bottom numbers are charged particles. So it looks like you've got a negative charged particle here. That's a beta particle. So the numbers at the top have to add up. So 234 on both sides, and the bottom numbers have to add up to 91. So 92 minus 1 is equal to 91. So the top number is mass, and the bottom number is charge. So mass is the top, and charged particles are at the bottom. So mass must be conserved in numbers, and charge must be conserved as one of the principles of physics. Just like energy, we say, can never be created nor destroyed. Well, in these nuclear equations, the mass number must be balanced, which it is. 234 equals 234 plus 0, because the beta has no mass to that level of integer, to the nearest integer. Okay, so that's how the mark scheme is laid out, and here's the question. So let's have a look at what they want us to do. Protactinium is an element with several different radioactive isotopes. So this is topic 7, radioactivity. It goes through theory first, and then it's got some investigation skills covered in this question too. Protactinium-234 has a half-life of 6.7 hours, which is how fast it decays. So every 6.7 hours it goes down by half the activity as the isotope nuclei decay. A sample of protactinium-234 has an initial activity of 800 units, okay? And they want you to put the units, give a suitable unit for the activity. Well, the answer is becquerels, and that means the activity per second, how many of the nuclei are disintegrating or decaying per second. So that's 1 mark. On the axes, sketch a graph for the decay of the sample of protactinium-234 during its first 3 half-lives. So you see 3 half-lives would be about 20 something hours. So because 6.7, so I think it'll be exactly 20 hours. And it should be a smooth curve, which it is. And you need to start with 800 at time 0, okay? And then after the first half-life, which should be about 6.7 hours, so it'll be just below 7. So I put 7 there. So I've drawn it as accurately as I can on this scale to show that after 6.7 hours, here would be 6.7 hours, just below 7. If you do with a narrow pencil, you'll be able to work it out. And then after another 6.7 hours would be 13 point something. Then it'll be down to 200 because it's halved again. And after another 6.7 hours, which will be about 20, it'll go from 800 to 400, from 400 to 200, from 200 to 100. And that's what half-life means. And here I should have put becquerels, okay? Because the activity is in becquerels, okay? So, something I forgot to do. Let's do it now. Okay, there it is. All right, then it says, when protactinium undergoes beta minus decay, it becomes uranium-234. Well, what happens in beta minus decay? It means there's too many neutrons, and one neutron decays into a proton and a fast-moving electron, which is what a beta minus particle is. Okay, the incomplete nuclear equation shows this process, and they want you to fill in the missing numbers. So what I told you when we look at the mark scheme, it's got to be 91 on the left because we've got 92 in the uranium. Beta has a charge of -1, and this is the only decay where you get a negative number in the GCSE. Okay, so 92 minus 1 will leave 91 protons. So basically the proton number has increased by 1 because, remember, one neutron decays into a proton. So proton number goes up by 1, neutron number goes down by 1, but that means the total mass doesn't change because neutrons and protons to 0 decimal places have exactly the same mass. Electrons will have 0 mass. I actually made a mistake here and just wrote 234 without thinking. Okay, so you get 1 mark for the top numbers balancing and 1 mark for the bottom numbers balancing. Okay, so I've done that, got the 2 marks here. And the next bit of the question, it mentions that a student suggests an experiment to determine the type of radiation emitted by a different isotope of protactinium, this time protactinium-231, and this is his suggested method. Step 1, connect a suitable radiation detector to a radiation counter, so that will be a GM tube, Geiger-Müller tube. Step 2, place the source, at a fixed distance, 3 centimeters as we suggested, from the Geiger-Müller tube, the detector, and that means they control the distance to make it a valid or fair test, because presumably they're going to do it more than once. So you keep the source at a fixed distance, that's a controlled variable. Step 3, record the count of the detector radiation for a time of 1 minute. Again, another controlled variable to make sure that your period of measuring is long enough to be able to get a reliable reliable data. Step 4 then says place a sheet of paper between the source and the detector, and paper is a good test to see if alpha is given off, because if it can be stopped by paper, then it's got to be alpha radiation, because beta can go through paper and so can gamma. Okay, so that's why they first do it with paper, and presumably they would then record the data with the paper in the way. Step 5, they then record the count, exactly, with the paper in the way for, again, a count of 1 minute, because that's our controlled variable. Each time we're doing it for 1 minute to make it fair or valid. Step 6, repeat these steps 4 and 5 first using aluminium and then a sheet of lead. So remember, aluminium can stop beta, yeah, and lead can largely stop gamma. So you remove the paper and use aluminium, and then you use a sheet of lead, okay? And that's what they did. So the table shows the results of the investigation done by a teacher. The independent variable is the material and how it affected the count rate. So the count rate is the dependent variable. With no material present, the count rate was very high. With paper, it shot down from 261 to 14. That means alpha particle was present. And then when you did aluminium, it didn't really decrease very much compared to paper. And in fact, with lead, it went up. And this could just be due to the uncertainty of the reliability of the instrument. So that variation can be largely ignored. Okay, so then it says which of these is the dependent variable. The dependent variable is the count rate because it's what you measure when you change the material. So A is the answer. Okay, so all aluminium, paper and lead all reduce the count rate to more or less the same value. There's something they did wrong, which they're now going to go into. Okay, the students' method does not allow for the background radiations. Remember when I taught you, if you're one of my students, that there's background radiation everywhere on Earth. It comes from the food, it comes from you and me. Everything living has some radiation in it. Radiation is a part of nature. So if you did not allow for the background radiation, that's like you've got a zero error, and that will be a systematic error in your data. Okay, that means it will always be there. It's not a random error. That could be positive or negative. It could have a positive effect or a negative effect on the number. Describe how the student's method should be modified, which is an evaluation skill, yeah, how to improve an experiment, to allow for the background radiation. So you should remove the source. So don't do the measurement without the source first. Measure what the background radiation level is in the room at the count rate. Again, to be fair, keep the 1 minute to be valid. So measure the count rate without the source there. Will get you 2 marks, and then subtract what you consider to be the average background count level in the room from all your results in the table. Okay? And then you would see what the data would decrease by. Say your background count is 9 or 7 or whatever, you then take 7 off all these results. Okay, so you should always account for background radiation first. Unfortunately, we don't have the equipment in the school to do it, so you become more familiar with it when you do the exam questions. Then it says describe how the student's method could be modified to improve the reliability of the results. Well, they didn't take any repeat readings, so that's the best way of doing it. Obviously, repeat the readings at the same 1 minute count rate and determine the mean value to get the 2 marks. So whenever you say to repeat, you're doing the repeat to get an average or a mean value. Remember, mean is the kind of average you want to take, yeah, not a mode or a median. So mean is the better word to use. It's good training for A-level. Evaluate the data from the experiment to conclude the type of radiation emitted by the protactinium. Well, we've kind of already said from my discussion that it must be alpha, as even paper reduced the count rate substantially to near the background level, at least if we'd measured it. It was certainly very low because it was like 10, 11, 12, 13, 14, in that range, all of them, as confirmed by the fact that aluminium and lead did not reduce it significantly more compared with paper. So therefore the conclusion is that it must be alpha. The underlined bits at the top give you 2 marks, and the final bit is the bottom line. So we get 3 marks. Another 15-mark question, yeah, that you've just gone through. Okay. Here's the rest of the mark scheme. Here's got like a note here about pointing the source away, safety point of view, to keeping the source in the box to increase in distance and make sure it's not affecting the count rate. Okay? Can't think of anything else that we need to look at. Both must be mentioned for this mark. Count significantly decreased due to the paper. No additional effect when using aluminium and lead. Exactly what we wrote. So radiation must be alpha. Yeah. Yeah, so they're saying the idea that the count rate with aluminium and lead is the background radiation. So because effectively that would stop all radiation going through. So the background would be in the range of what we measured with the lead, for example. Okay, question 8. Let's see if we can work out what it's about. Yeah, it's a curve. Speed is not constant. Okay. Looks like it's to do with some kind of oscillation, peaks and troughs. Yeah, so let's have a look. Okay, this diagram 1 shows a set of masses attached to a spring which is suspended from a support. Okay, so it looks like it's to do with stretching a spring, so that will be Hooke's law. It's topic 1, forces, but I think it must be oscillating because we saw peaks and troughs. So after the masses are added, the length of the spring is 14.6 centimeters. The student measures the extension in the spring as 11.5, and they want you to calculate the original length. With the original length, there's a difference between these two readings. Yeah, the extension, so that means 14.6 when you've added the weights. Take off the extension, the original length was 3.1 centimeters. I just made a mistake when I just worked it out in my head. I think my brain wasn't working. The units are provided. The student removes the masses and notices that the spring does not show elastic behavior. It means it doesn't return to its original length. Predict a value for the new length of the spring after the masses have been reviewed. Well, they will accept any value between the maximum 14.6 and say 3.2. Yes? It's not going to return to the original length, which was 3.1. It must be greater than 3.1. And if you plot a graph, you can see how the graph should look. Okay? In other questions, they often give you the graph. In this one, they haven't. The student then puts the masses back on the spring and then pulls the masses down and releases them, and this is creating an oscillating system. The masses vibrate up and down in a vertical direction as shown in the diagram. So the vibrations are up and down. Yeah. And the distance time graph shows how the distance between the top of the masses and the support changes as the mass vibrates. So obviously it gets to a peak, then a trough, a peak, then a trough, a peak, then a trough. These are the turning points for the oscillating mass spring system. Explain how the gradient of the graph shows that the masses accelerate as they vibrate. Well, if the distance is against time, the gradient of the graph will be speed. Now, the gradient isn't constant. The gradient changes. Here is negative, here is positive, here is negative, here is positive, here is negative, here is positive. And also, the steepness of the gradient also changes, which means if the gradient of the graph is the speed or the velocity, and since the gradient is not constant, we know the velocity is not constant, and if the velocity is not constant, then there must be some acceleration going on. Okay, actually keeps on changing direction to change velocity, and therefore it must be accelerating back to the center of the oscillation each time you displace it. In A-level, we call this simple harmonic motion. So add crosses x to the distance time graph, which I did, to show all the times when the masses are not moving. So every time it changes direction from going up to down, so when the mass goes down here, it stops for a second before returning up, and then it stops here and then goes down. So it keeps on going up and down. And at the end points here and here, momentarily, its velocity will be 0. Okay? And these points are the turning points on the graph. So that's what I've put here. If I just put one of these, I'll get 1 mark. If I put all of the turning points, yeah, all 6 of them, I will get 2 marks. These are the 6 points where the object is turning, and therefore it shows times when the masses are not moving. Okay, so that's how you get the 2 marks. Put all 6 x's. All right, so that's question 8 done. Question 9 is again about forces. Very big topic. The driver of the racing car makes a pit stop during a race to change the tires. The area where the tires are changed is called the pit lane. You've probably seen this in Formula 1 racing. Before entering the pit lane, the speed of the car must decrease, obviously, so it doesn't kill anyone for safety reasons. The mass of the racing car is given in kilograms. The maximum braking force is 41,000 newtons. So that's the braking force. So that they want you to show the maximum deceleration. So the maximum deceleration will be when you're using the maximum braking force on the mass, and then you have to show it mathematically. That gives you an answer of 50. Okay, so remember that you want to work out acceleration. So acceleration is force over mass. So maximum braking force is mass times maximum deceleration, which comes from Newton's second law. Change the subject to A. 14,000 divided by 830 gives you 49.4 to 3 significant figures, which is approximately 50 to 1 significant figure. Okay, rounded up, which is what they've asked us to do. So we have shown it. Remember, show that means prove it mathematically. Then says the racing car is traveling at an initial speed u of 72 meters per second. Calculate the minimum distance needed, that's s in our equations, constant acceleration, to decrease the speed from 72, not to 0, but to 26. So v will be 26. Use the equation v squared equals u squared plus 2as, which is the one that GCSE students find the most difficult. We know the acceleration is negative 50 from before, approximately is fine. So if you want to put the numbers in there, you could put these numbers in there, or I've changed the subject to make s the answer. So that will be v squared minus u squared over 2a. If you're good at maths, you can do that algebra. That'll be 26 squared minus 72 squared divided by 2 lots of minus 50, because 2a, a is negative. This will give you, the top will give you a negative answer. The bottom is minus 100, which will give you 45 meters if you put in the calculator to 2 significant figures. So these questions students find very difficult. So you just got to practice them before your real exam. They come up reasonably regularly. Okay? All right, so the next part. It says the racing car slows down using its brakes. The brakes use friction, and the brakes become very hot when the car slows down. Use ideas about energy, explain why the brakes become hot. Okay, well, work done by friction in the brakes, yeah, obviously in the brakes, is a kind of mechanical energy transfer. So the work done is transferring energy mechanically from the car's motion to the thermal energy store of the brakes. So this causes the kinetic energy of the car to decrease, the friction, and the thermal energy store of the brakes will increase as a result. Okay, so these 3 lines get you the 3 marks. Hope that makes sense. The tyres of the racing car also get very hot during a race. A mechanic has to handle the hot tyres during a pit stop. They wear protective gloves, which have several layers of insulating materials. Well, what does that do? It reduces heat transfer. So you already know they're going to ask about reducing heat transfer by what? By conduction. Okay? So that's in solids. Explain how the layers of insulating materials, obviously in the gloves, reduces the risk of the mechanic burning his hands or her hands on the hot tire. All right, so any 2 points from here. Insulating materials are poor conductors of heat. The different layers trap air, and air is a very good or effective insulator. Okay, trapped air. So energy transfer by conduction is reduced. And this means that many layers or thickness of material reduces the rate of heat transfer to the person wearing the gloves. And that's a way of explaining thermal energy transfer or controlling the rate of heat transfer using insulation. And that's 11 more marks. Question 14 is about a structure of a dam designed to hold water in a reservoir. That's topic 5, solids, liquids and gases. Pressure of the water in the reservoir. The dam, you'll notice, is thicker at the bottom because that's where the pressure is highest. The water in the reservoir has a depth of 35 meters, which I've drawn here. And state the formula linking pressure difference, height, density, and gravity, which is 10 newtons per kilogram on Earth. So that'll be P equals H for the height, rho for the density, and G for gravitational field strength. 1 mark for knowing what each letter stands for and putting it in the right order. Atmospheric pressure above the water, so at the surface of the water, is already 100 kilopascals, so that's due to atmosphere, the air. So that is above the water, that's extra pressure that you've got to be aware of. Calculate the total pressure at the bottom of the reservoir. So the total pressure is obviously the atmospheric pressure of the air above it, plus the water pressure at 35 meters of depth. You need to know the density of the water, which is, for pure water, is 1,000 kilograms per meter cubed. So that's how you work out the total pressure. So let's just work out the water pressure first. So the water pressure is P, which is 35 times 1,000 times 10, using the equation we quoted above. 35 height times 1,000 density times 10 gravitational field strength give you 350,000 pascals, or 350 kilopascals. Every 10 meters of water is equal to 1 atmosphere, I teach my students. So total pressure here is equal to 350 kilopascals due to the water, plus 100 kilopascals due to the air, gives you a total of 450 kilopascals, and they want the units in kilopascals, which is what I've done. Okay? And the next bit, it says an underwater camera is used in the water reservoir. The camera lens experiences a force of 430 newtons at a pressure of 260 kilopascals. So that would be 260,000 pascals. State the formula linking pressure, force, and area. So they've given us the force, they've given us the pressure. Presumably, they want us to work out the area. So if you put in a triangle, there's the triangle. Calculate the area of the camera lens. So make A the subject, A is F over P, 430 newtons, divided by 260,000 pascals, gives you an area in meters squared of 0.00165 to 3 significant figures, and they want you to give the units. Well, if you're using newtons and pascals, it will be meters squared, so 1 mark for the unit and 1 mark for probably giving it to 2 significant figures, because that's the data that is best is used in the question. Then they say seawater has a density slightly more than pure water, so that's 30 kilograms per meter cubed more than pure water, 1030. Explain how the design of the dam would need to change to hold the same depth of seawater safely. Okay, well, if the pressure is going to be increased by roughly 3%, the pressure would increase due to the water by approximately 3%. 1030 is 3% more than 1000. Therefore, the dam would need to withstand this increase of 3% by having a wider base. Remember, the concrete at the bottom is what is withstanding the pressure, because pressure acts in all directions, and that gives you 11 marks. Question 10. Question 11 is the gravitational field strength of a planet decreases with increasing distance from the planet. Yeah, so further you are from the source of gravity, the weaker it is, a bit like the magnets. It's a non-contact force. So this is from astrophysics, topic 8, the last topic in GCSE. The table shows the value of the gravitational field of strength of Mars at different distances from the center of Mars. Okay, so they go from 4,000 kilometers distance to 9,000 kilometers from the center of Mars, and the gravity in newtons per kilogram never reaches the full gravity of Earth, which is 10. The maximum is 2.6, and the minimum is 0.53 at 9,000. So it does decrease, as they said. They then say a student finds this formula in a textbook. What formula? This formula. Okay. Well, if you do A-level, you might recognize that it's pretty close to the correct one. It links, this formula links distance from the center, the first column of the table, to the gravitational field strength of the planet. Okay, so the gravitational field strength of the planet multiplied by the distance squared, they're saying should be equal to a constant. Okay, so use the data from the table to see if this formula is correct. To justify this formula means to see if it's correct. So what you've got to do is you've got a calculation, for example, do the calculation from the first column, 2.66 from the first row, I should say, times 4,000 squared. That gives you a value of 42,560,000 or whatever units they are. You don't need to worry about it. So that's the first calculation. And if you do it for all of these values, you'll see it varies from 42,560 down to 42,800. That seems to be lower, and the maximum is 42,900, but that could be due to uncertainty in your data. So they're all about 42 to 43,000. So you see, if you do 2 calculations, you get 2 marks. If you do all of them, obviously, it shows you know what you're doing. See the table, the constant is between 42.5 and 43 million random units. You don't have to worry about the units. Okay, it's actually got kilometers in it. If we wanted in SI units, we would have had to change it to meters, but it's not worth doing mathematically. So you can then say, because they're all about in the same range, the formula is justified. Quite accurately, I've put, based on the figures provided. Yeah, actually, it's more or less correct to 2 or 3 significant figures. Okay, so that's pretty accurate. And then it says, Olympus, this is the last question in the exam paper, so you'll be pleased to know you won't have to listen for much longer. If you've managed to listen to it all in one go, I'll be amazed. You've probably stopped the video several times, done the questions you wanted, gone and had snacks, gone and done something else. That's the way you should do it. You pause, take short breaks, come back, and you could listen at double speed, as I said. and then just do your corrections to your own paper. So it says in the final part of the exam, Olympus Mons is the tallest mountain on Mars. The distance from the center of Mars and the peak of the Olympus Mons is 3,410 kilometers. Calculate the gravitational field strength at the peak. They want you to use the data that you just used in the table from that equation, where we know that the constant that we'd worked out was about 42 to 43, so the average would be about 42.7. So if you do 42.7 divided by d squared in that formula, you should be able to get the gravitational field strength. Yeah, so if we do it for the mountain, the top of the mountain, the distance would be 3,410 kilometers, and we get the average value from the data in the table that I just showed you. You'll get gravity to be about 3.67 newtons per kilogram at the peak of the mountain to 3 significant figures. Okay, I think 3 significant figures is correct, because you can see we know the distance to 3 significant figures, and the average I've used for the constant is also to 3 significant figures, and that ends this run through. 7 marks for question 11. I hope you found it useful. The mark is out of 110. If you mark it yourself, and because it's a 2023 paper, you can actually look up the grade boundaries and see roughly what mark you would get if you're doing double science, if you get the same average score for biology and chemistry. So it gives you an indication of the grade you're heading towards. If you're doing physics, you'd have to add it to your paper 2 as well. So you'd need to do paper 1 and 2, and then look at the grade boundaries for the physics. So hope that makes sense to you. If you found it useful in any way, please support the channel, give us a like, share it with your friends, and make sure you subscribe, ready for the next video. As I told you at the beginning of the video, I'll be doing some more run-throughs in the build-up to the GCSEs. Thanks for watching. Catch you in the next video. Bye for now.